So this is video number 31 on my serial variable calculus 2. In this video, we're going to talk about polar form of a complex number. In the previous video, we talked about the standard form of a complex number, which is the form a plus bi. And we talked about how to plot points on the complex plane. We have the horizontal axis, which is the real axis, and the vertical axis, which is the imaginary axis. The horizontal axis is basically the x-axis, and that is equal to r, which is the distance to the origin, times cosine of theta by the formula for the polar coordinates. And b, which is the vertical coordinate, is r times sine of theta. So that tells us that z is going to be a, which is absolute value of z cosine of theta, plus I times absolute value of z sine of theta. So we can rewrite that as z equals absolute value of z times cosine of theta plus I sine of theta. This guy is called polar form of a complex number. Now there's a very interesting relation between cosine, sine, and exponential. Let's write down what this gives us using the Taylor series for cosine and sine. The Taylor series for cosine was the sum -1 to the power of n over 2n factorial x to the power of 2n, n equals 0 to infinity. And the Taylor series for sine of x centered at the origin was the sum n equals 0 to infinity, -1 to the power of n over 2n plus 1 factorial x to the power of 2n plus 1. We're going to plug in n equals 0, 1, 2, 3, 4, etc. And we'll write down both sine and cosine. We'll multiply sine by I, we add it to cosine and see what the terms are. If you plug in n equals 0, we get -1 to the power of 0, which is 1 over 0 factorial times x to the power of 0. The next term is -1 over 2 factorial and then times theta to the power of 2. And the next term is theta to the power of 4 over 4 factorial. The next term is theta to the power of 6 over 6 factorial plus minus etc. At the bottom, we get theta over 1 factorial minus theta cubed over 3 factorial plus theta to the power of 5 over 5 factorial minus theta to the power of 7 over 7 factorial, and again plus minus plus minus. And these are when you plug in theta n equals 0, 1, 2, and 3. Now let's evaluate cosine of theta plus I sine of theta and see what we get. Well, the first term is the constant term, that is 1. The linear term comes from sine, so that is plus I theta over 1 factorial. The quadratic term comes from cosine, so that's minus theta squared over 2 factorial. Cubic term comes from the sine, negative I theta cubed over 3 factorial, and then plus theta to the power of 4 over 4 factorial plus I theta to the power of 5th over 5 factorial minus theta to the power of 6 over 6 factorial minus I theta to the power of 7 over 7 factorial. As you see, the pattern is plus plus minus minus plus plus minus minus, so the next two terms are going to be plus, etc. Now let's see if we can find a relation between this one and exponential. Let's look at the coefficients. Coefficients that are 1, I. Now -1 is I squared, so I squared is -1. Negative I is I cubed, so I can write this down as I cubed. Now the next one is I to the 4th. I to the 4th is 1. I to the 5th is I to the 6 is -1, and I to the 7 is negative I, etc. So that means I can write this down as 1 plus I theta over 1 factorial. The next one is I theta squared over 2 factorial. The next one is I theta cubed over 3 factorial. The next one is I theta to the power of 4 over 4 factorial. The next one is I theta to the power of 5th over 5 factorial. Then I theta to the power of 6 over 6 factorial. I theta to the power of 7 over 7 factorial, etc. Now, if you recall, we had the power series expansion for e to the power of x, which was the sum x to the power of n over n factorial, n equals 0 to infinity. That's exactly the power series for exponential, except x is replaced by I theta. So this tells us that we can write down cosine of theta plus I sine of theta as e to the power of I theta. And this formula is called Euler's formula. Now, if you look at this formula and replace the form that we found for z, which is called the polar form, we would get z is equal to absolute value of z times e to the power of I theta. And that's called the polar form. You can either write it down like that, or you can write it down as absolute value of z cosine of theta plus I sine of theta. Now notice that because cosine and sine have period 2 pi, if I change the angle by 2 pi, if I increase or decrease the angle by multiple of 2 pi, then the expression cosine theta plus I sine theta or e to the power of I theta does not change. In other words, e to the power of I alpha and e to the power of I beta are the same whenever I alpha minus beta is a multiple of 2 pi. So keep that in mind. In other words, we can change the angle, but we cannot change the absolute value. Let's do two examples on polar form of a complex number. Write down each complex number in polar form. So we'll graph this one on the complex plane. So the first one is 1, positive 1, and then negative I, so which is here. So we're going to have to find the angle here, and that would be our theta, and then we have to find the absolute value as well. So the absolute value is the square root of 1 plus 1, which is root 2. The angle, which is this angle here, is in the negative direction, and it is pi over 4. So that tells us that z is equal to root 2 e to the power of negative I pi over 4. But we can write it down in other forms as well. You can write it down as negative root 2 e to the power of, you can write down, you can use this angle, which is 2 pi minus pi over 4. So I 7 pi over 4 is another way of writing this down. Or we can do root 2 e to the power of, we can add 2 pi to that, 7 pi over 4 plus 2 pi, etc. So there are multiple ways of writing this down. This is one way of writing it down in polar form. So the next part of this problem is asking us to write down negative 3 minus 4i in polar form. So if you look at negative 3 minus 4i, we can see that that point is in the third quadrant because the real part is negative and so is the imaginary part, that both of those are negative. So the angle is right here. So in order to find this one, I'll have to use arctangent, and I can say, well, if I call this angle alpha, which is the same as that alpha, so tangent of alpha is going to be opposite, which is 4, divided by adjacent, but this angle is between 0 and pi over 2. So we can say this angle is tan inverse of 4/3. But the problem is that's not exactly the angle for this point. This is the point W. This angle is the angle I'm looking for. So in other words, theta, which is the angle for W, is tan inverse of pi over 4/3 plus pi. Or you could say tan inverse of 4/3 minus pi as well. So this angle is also another way of looking at that. So that means I can write down W as absolute value of W e to the power of tan inverse of 4/3 minus pi times I. This would be one way. And what is absolute value of this W? Well, W is negative 3 minus 4i. So absolute value of W is going to be square root of 9 plus 16, which is 5. So we can write it down as 5 e to the power of tan inverse of 4/3 minus pi times I. This would be one way of writing down this W in polar form. Notice that when you have polar form of a complex number, you can multiply the e to the power of I alpha and e to the power of I betas by just adding the exponents. We have still the rules of exponent. Now let's use that polar form to find z to the power of 2025. We can find large powers of a complex number using the polar form. So let's write down this complex number in polar form. We have the x component is 1/2 and the y component is negative root 3 over 2. So we'll have to find this angle. Well, if you look at this right triangle, this is a 30, 60, 90 triangle. Opposite is root 3, adjacent is 1 if you double everything. So that means this angle theta is in fact negative pi over 3 because it is tan inverse of root 3, which is pi over 3, but it's in the negative direction. Let's find the distance of this complex number to the origin. That's the square root of 1/4 plus 3/4, which is 1. So we can write down z as e to the power of negative pi over 3i. Now the question is asking us to find z to the power of 2025. So we can write down this as e to the power of negative 3 pi over 3 times 2025i. Now let's divide 2025 by 3. We get 6, 18, 2025. So 7, 21, 15, and 5. So this gives us e to the power of negative 675 pi I, which is, I can change the angle by multiples of 2 pi. So this is the same as negative pi I, which is cosine of negative pi plus I sine of negative pi. Sine of negative pi is 0. Cosine of negative pi is in fact negative 1. So the answer to this one is in fact negative 1. Write down the complex number e to the power of 1 plus pi over 2i in standard form. So let's go ahead and do that. So e to the power of 1 plus pi over 2i can be written as e times e to the power of pi over 2i. Now this would be e. We have cosine of pi over 2, which is 0, plus I sine of pi over 2. Cosine of pi over 2 is 0. Sine of pi over 2 is 1. So this whole thing becomes e times I. Okay, we can also use polar form of a complex number to find roots of a complex number. You want to find fourth roots of 16 in this example. So what do we need to do? We need to find 16 in polar form. Well, let's draw that on the complex plane. 16 is on the real axis, and it's also the positive part of the real axis. So the angle is 0. So that's what we have. Now, if I want to find the fourth root of that, I'll have to raise the exponent to 1 over 4. So 16 to the power of 1/4 is 2. And then I can divide the exponent by 4. So I get that. Now, we can change the exponent by 2 pi. We can write it down as 16 e to the power of 2 pi I. Fourth root of 16 is 2. And then e to the power of pi over 4i. Or we can write this down as 16 e to the power of 4 pi I. Or we can write it down as 16 e to the power of 6 pi I. Now, raising the exponents to the power of 1/4, we get e to the power of pi I. The next one is 2 e to the power of 3 pi I over 2. Now I have to plot them on the complex plane. The first one has the angle of 0, so that's the first one, and the distance to the origin is 2. The second one has angle, in fact, this would have to be pi over 2, angle pi over 2. So it would be right here, and the distance to the origin is 2, so that's 2i. The next one, angle is pi, and the distance to the origin is in fact 2 again. And the third, the last one, the angle is 3 pi over 2, and the distance to the origin is 2. So these are all fourth roots of 16. In general, if you want to find nth roots of a complex number c, what you do is you write down the complex number c as absolute value of c, e to the power of I theta. Then you raise it to the power of 1 over n, which means you take the nth root of absolute value of c, and then you divide the exponent by n. You get nth root of absolute value of c, e to the power of I theta over n. However, you can change the exponent by multiples of 2 pi. And if you do that, you get new nth roots of unity, and then after n, it keeps cycling through the same number. So in other words, you get nth root of absolute value of c, e to the power of I theta plus 2k pi over n, and k ranges from 0 all the way to n minus 1. If you get to n, you go back to the case where k is 0. So let's do a couple of examples on this one, and then we will summarize. And this is really the last topic that we are going to talk about in this class. Find all third roots of negative I. The first thing we're going to do is we are going to place negative I on this plane. So negative I is right here. So what are the third roots of negative I? First, we have to write down negative I as the distance to the origin is 1, and the angle is 3 pi over 2, and then times I. Then we are going to take the angle and we're going to divide it by 3. So let me write this down as e to the power of 3 pi over 2 plus 2 pi, and then I. And then the next one is e to the power of 3 pi over 2 plus 4 pi, and then times I. Let's take the third roots. So third roots of negative I are going to be, the first one is e to the power of pi over 2I. So we'll have to take the distance of 1 to the origin and angle of pi over 2. So it is in fact I. So that's one of the third roots of negative I. The next one, you have to take the angle, which is 7 pi over 2. And we'll have to divide that by 3. So we get 7 pi over 6. So that would be an angle of pi plus pi over 6. So it is this one. So this would be e to the power of 7 pi over 6 times I. The next one is we add 2 pi, we get 8 pi plus 3 pi, that's 11 pi over 6. So we get e to the power of 11 pi over 6 I. And that would be basically the reflection of the same thing on the other side. So this would be e to the power of 11 pi over 6I. These are the three third roots of negative I. And if you look at the angles that they make, they are making the same angles. This angle is pi over 2 plus pi over 6. This angle is pi over 2 plus pi over 6. This angle is also the same thing. It is pi minus 2 pi over 6, which is pi minus pi over 3. And that's the same thing. That's like pi over 2 plus pi over 6. So they make the same angle with each other. So these are the three third roots of negative I on the complex plane. Now, if you want to write them down in standard standard form, you would have to write down the first one as I. The second one is cosine of 7 pi over 6 plus I sine of 7 pi over 6. And the third one is cosine of 11 pi over 6 plus I sine of 11 pi over 6. So let's see what they are. So they are I. Cosine of 7 pi over 6 is going to be root 3 over 2, but it's in the third quadrant. So that would be negative of that, negative root 3 over 2, and then minus I over 2. So the next one, cosine is positive, so root 3 over 2, and sine is still negative, minus I over 2. So these are the three third roots of negative I. The last example is to find roots of the quadratic equation. So we can use the same quadratic formula that we have learned in algebra 1. So we're going to move everything to the same side. We get z squared plus 2z plus 1 plus 4i equal to 0. Next, we're going to use the quadratic formula. So we get minus b plus or minus root b squared minus 4ac. So we get all of that divided by 2, we get minus 2 plus or minus root minus 16i divided by 2. So what we need to do is to find roots of negative 16i. So let's plot negative 16i. Negative 16i is right here. So this is negative 16i. So the angle is in fact 3 pi over 2, and the distance is 16. So we can write down negative 16i as 16 e to the power of 3 pi I over 2. And if we add 2 pi to the angle, we get 7 pi over 2 times I. Now we can take the square root. So the two square roots are going to be 4 e to the power of 3 pi I over 4 and 4 e to the power of 7 pi over 4 times I. Let's evaluate these. The first one is 4 times cosine of 3 pi over 4. 3 pi over 4 is in the second quadrant, so cosine is negative, negative root 2 over 2. And sine is positive, so plus root 2 over 2I. And the other one is 4 times, well, cosine is positive, so root 2 over 2, and sine is negative, minus root 2 over 2I. So that's what we get for square root of negative 16I. Now we'll have to take these and plug it into the formula. We get z equals minus b plus or minus these two things, but in fact these two are just negative of each other. If you look at the first one, that's the negative of the second one is negative of the first one. So we can just replace one of them. So we get negative 2 root 2 plus 2 root 2I, all of that over 2. Now the 2's simplify, we can simplify this 2, so we get negative 1 plus or minus negative root 2 plus root 2I, which gives us the two roots of negative 1 minus root 2 plus root 2I. This is one of the roots, and the other root is negative 1 plus root 2 minus root 2I. These are the two roots of this quadratic equation that they gave us. So to summarize, we learned how to write down a complex number in polar form. We first find the absolute value of the complex number, then we find the angle that OZ makes with the positive real axis. So we get z is equal to absolute value of z e to the power of I theta. E to the power of I theta is cosine of theta plus I sine of theta. We can also use laws of exponents. To find the large power of a complex number z, we write down z in polar form. Z equals absolute value of z e to the power of I theta. Next, we will take z and we raise it to the power of n, and the way we do that is we raise absolute value of z and e to the power of I theta to the power of n. Note that you can reduce the angle n theta by any multiple of 2 pi. That simplifies the problem. To find nth roots of a complex number, we write down the complex number as absolute value of c e to the power of I theta. Then we divide the exponents by n. We get nth root of absolute value of c e to the power of I theta over n. And then we keep adding multiples of 2 pi to theta to get nth roots of c. And that brings me to the end of this video. I will see you in the next video.